All right, today we have our first quiz. Again, it's open book, open note, open computer. It'll cover, what we've not everything, but it's from the topics that we've covered over the last week. I'll give you plenty of time at the end of a lecture today to get it done, maybe 40, 45 minutes. But we will cover material up until that point. And once you're done with the quiz, of course, feel free to leave, turn it in up here. And if you get done with it early, go ahead and take off if you need to. Otherwise, also remember that homework 1 is due on Monday. The written portion is due in class, and the programs are due by midnight on Monday evening. So keep that in mind. A couple more, or actually just one more problem that I wanted to address as far as divide and conquer strategies go. Because again, it fits nicely in what we've been talking about of divide something, you conquer it, and then you combine solutions. But also the way that you get efficiency out of that is by looking for structures or patterns that you can exploit. And a lot of times it's just mathematicians writing stuff out, writing stuff down like Karatsuba did with the FOIL rules, realizing that you can get away with only 3 multiplications instead of 4 multiplications. At the expense of some additional additions and subtractions. Same idea with matrix multiplication here. Before we look at the algorithm that's divide and conquer, let's remind ourselves what matrix multiplication is. Given 2 matrices, and for the first example here, I'll just go ahead and write a simple 2 by 2 matrix, A, B, C, D. Right? So it's a 2 by 2 matrix, and we can multiply that by another 2 by 2 matrix, E, F, G, H. Right? And think of these as actual numbers. The way that you go about computing this is you take the first row and then you take it and component-wise you multiply all the components in the first column. So it will be AB times EC. So A, E, B, BG, right? And then you add those together. And that gives you your 2 by 2 matrix multiplied by a 2 by 2 matrix is going to result in a 2 by 2 matrix. We're only going to consider square matrices here. I'll talk about how to deal with non-square matrices after we've looked at this algorithm. But that gives you your first component. That gives you the upper left component here. Now to get the upper right component, you go AB times FH. So A, B, F, H. And then you add that together. And then for the bottom left component, now you go on to the second row and multiply that by this column over here. So CE and DG. Right? And then for the last component of the bottom right over here, it's CD times FH. So C, D, F, H. Right? Now that's just for a 2 by 2 matrix. For a 3 by 3 matrix, you'd have 3 elements in the first row that you would multiply 3 elements on the first column. 3 elements on the first row, and then the second column, third column, etc., etc. In general, if you have an n by n matrix, right, multiplication, say that A is an n by n matrix and that B is an n by n matrix, it results in another matrix, C, n by n matrix called C, where each component, C sub ij, is going to be a big summation of I running from, do I want I? I want K, sorry. K running from 1 up to n of AI K times BKJ. And that's just a fancy way of writing that your A sub i's here are coming, the ijth entry in your matrix over here is corresponding to the ith row in the first matrix and the jth column in the second matrix. And you take all n of those things and then you multiply them together in the column. Right? What I want to focus on is how many multiplications are there and how many additions are there. So let's look at this example up here for a 2 by 2 matrix. How many multiplications did I end up doing over here? 1, 2, 3, 4, 5, 6, 7, 8. Right? How many 8 multiplications? How many additions did I end up doing? 1, 2, 3, 4. 4 additions. Now let's think more generally. Let's just look at one entry, say theCijth entry here in C. That's going to be equal to, and we'll map it back over here. I should have given myself some more room here. But we'll map it back over here to, in fact, you know what? Let me write it over here since I don't have enough room. This is going to map over here to A and B, over here. This is going to correspond to the ith row and the jth column over here in this second matrix over here. And we're going to take these and we're going to basically flip it over and multiply each one of those components. Now this is an n by n matrix. N by n. All three of these are n by n matrices. So how many elements do I have in here? N. And there are n elements over here. So for one entry, how many multiplications do I do? I take n elements over here and multiply each one of them to n elements over here. So there are going to be n multiplications. Now that bears out in this summation right here. For k running from 1 up to n, you're doing a multiplication once each time. So there are a total of n multiplications for each entry. Now how many additions am I doing? How many additions did I do over here for this one entry? Just one. One entry, one entry, one entry. So if I'm summing up n elements, how many additions am I actually going to be able to do? N minus 1. Because you're not, if you start out with the first element, right, you're not doing an addition for that, you're just adding all the other elements. So that's for one entry. How many entries are total? There are n squared total entries. All right? So what does that say about in total? There are going to be n cubed multiplications. And how many additions in total? Well, n minus 1 additions for each entry, and there are n squared total entries that you have to compute over here. So this is going to be n squared times n minus 1 additions. At the end of the day, both of these are going to be order n cubed. Right? So not that great of an algorithm, but that's what it takes maybe to do matrix multiplication. Can we do better? Can we take this cube here and can we take it down? Right? Now, before we do that, let's understand. What's our ultimate goal? What's the lower bound on this? Right? If I've got n squared elements in my input and n squared elements in my input, then I have to at least look at all the input unless I want to lose information, right? So I have to, my trivial lower bound on this problem is going to be order n squared, because you have to at least look at the input. So can we get it down to n squared? In other words, from the naive algorithm from n cubed, can we get it down to n squared? You might think that this is quadratic, but it's not. Again, we faced the same problem yesterday when we looked at binary exponentiation, right? The input was a number, but the input size was the number of bits required to represent that number. In this case, the input are two matrices. What is the input size? How big is one matrix in general? N squared entries, right? So if we're able to get it down to this is actually linear with respect to WRT, with respect to the input size. So don't think of this as an inefficient order n squared algorithm that we've already said that's not going to cut it, right? For all pairs, that's going to take way too long. Well, you've already resigned yourself to a large input, this large n squared size matrix. So if you're doing only n squared work, well, that's pretty good because that's linear. Right? And this is not quadratic. This is not even. I mean, the naive way of doing this isn't even quadratic. If it were quadratic with respect to the input size, it would actually be n to the fourth. So it's somewhere between linear and quadratic already. But can we get it down and can we do better? And the answer is yes. I don't have a year on this. I forget what year it was. But 635. Okay. Yeah, this is what I need. All right. So Strassen, the same Strassen that I mentioned yesterday, Strassen's matrix multiplication. The same Strassen that was helped to come up with a fast Fourier transform. He rewrote basically he rewrote these out and said, well, there's 1, 2, 3, 4, 5, 6, 7, 8 multiplications here. Very, very similar to what Karatsuba did, and rewrote everything and said, oh, I can take it from 4 multiplications down to only 3 multiplications. Does that help me? He just sat there and played with these identities and played with these identities until he finally came up with something else. That if I've got something like this, I'll label, this is a 2 by 2 matrix now, C00, C01, C10, and C11. I regret using 0 indexing now, but that's all right. Ultimately, I'll go ahead and rewrite these to be 1 indexing, A10 and A11. I've got my first 2 by 2 matrix here, and I will multiply that by B00, B01, B10, and B11. And again, normally it looks something like this, but of course A, B, C replaced with all the A's and the B's and their index values. What he did is he came up with another identity. And how did he do it? Well, I'm sure that he just rewrote it 100 times until he found something that worked. There's no insight here as to why this works, at least that I have, but it's just a bunch of identities that actually turned out to work. And these m's, I'll define these here in a second. M2 plus M4 over here for the lower left. The upper right is going to be M3 plus M5. And over here it's going to be M1 plus M3 minus M2 plus M6. So we've actually got 7 other values here that we have to compute. Those values are as follows. M1 is simply going to be the entry A00 plus A11 times B00 plus B11. All right? Now, as we're going along here, we can save it up to the end here, but as we're going along here, I want to keep track of how many multiplications we're doing, because over here, we already counted up 8 multiplications and 4 additions. If you just use the regular old matrix multiplication identities, then that's what you're going to get. What I want to do is I want to count up here the number of multiplications and the number of additions as we're going along here. Okay? So M2 is going to be A11 plus A10 plus A11 times B00. So, oops, I forgot to do it. There's only one multiplication here, and there's 2 additions over here. Okay? On this one, there's 1 multiplication and 1 addition. M3 is going to be equal to A00, and the order here does matter, B01 minus B11. I can't now if this were truly just a 2 by 2 matrix here, I could go ahead and reverse these because multiplication of regular scalar values is commutative, A times B is equal to B times A. But is that true for any old matrix? Is any matrix A times matrix B, is that commutative? No, you can't do that. So the order matters here. Keep that in mind. There's one multiplication, and even though this is a subtraction, I'm going to count it as an addition. Why? What is? How can I rewrite a subtraction as an addition? You add the negation, right? So it's the same thing. M4 is going to be A11 times B10 minus B00. So again, one multiplication and one addition. M5, M6, and M7. Make sure I have enough room here. M5 will be A00 plus A01 times B11. So again, one multiplication and one addition. And then we've got A10 minus A00 times B00 plus B01. And so we've got 2 additions. Again, we're counting subtractions as additions, and only one multiplication. And M7 is going to be A01 minus A11 times B10 plus B11. And so again, oops, I should have said 2 additions over here and 2 additions down here and one multiplication here. Okay? Now, also don't forget that you have 1, 2, 3, 4, 5, 6, 7, 8 additional additions. Right? Because once you've computed all 7 of these values over here, then you need to plug them over here, over here, and then you need to compute these additions and these multiplications. So in total, I have 7 multiplications, right? And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 18 additions. Okay? I wrote these as scalar values. It doesn't have to be. You can replace each one of these with a matrix and do it recursively. The way that you can do that is by simply taking A. If A is an n by n matrix, and B is an n by n matrix, what you do is you break it up. You break it up into quadrants. And this becomes a matrix, A00. This becomes another matrix, A01, A10, and A11. Likewise, for B, you cut them up into fourths. So A and B were n by n matrices. But now A00, etc., how big are those? Well, if I cut, this is roughly going to be in half. So it's an n divided by 2 by n divided by 2 matrix. Right? So how many entries were there up here? N to the n squared. How many entries are down here? N squared divided by 4. Right? Now, don't think of this 4 here as cutting it into a fourth. Right? Really, technically, if you want to analyze this algorithm, it's an n by n matrix. Go ahead and simplify it like I was talking about over here. That's not really the input size, or that's not really the performance of the lower bound. The input size is actually n squared. So if you look at it from that perspective, you're not taking this and cutting it into by a quarter. This is actually half as big. All right? Because again, it's going to be, this thing is equal to n divided by 2 squared. So you're really only taking it half as big. All right? Each one of these can be a matrix just like this. And so if you need to do a matrix multiplication of A00 time, let's say that this matrix the addition times this matrix multiplication, you recurse, right? You recurse on this part, and then you cut it in half again, cut it in half again, cut it in half again, until when? When do you stop this recursion? When you've got a matrix of size 1 by 1, in which case you've got the original definition of matrix multiplication here, right? Then it's just a scalar. Then it's if you've got A times B, then it's just regular old multiplication. Okay. So the thing is this a savings? Right? With Strassen's matrix multiplication, we've got 7 multiplications and 18 additions, versus regular old matrix multiplication with 8 multiplications and 4 additions. What have we done? We've more than quadrupled the number of additions at the savings of only 1 multiplication. Is that a big deal? I don't know. Which one of these is more expensive? Is multiplications more expensive, or is additions more expensive? Which one of these operations in general is more expensive? Multiplications, right? So if we can save 1 multiplication, maybe that's worth paying 14 additional additions. Maybe. We need to do some analysis here. Now, this is going to be a recursive algorithm. So here are our observations. I'm going to let m sub n be the number of multiplications by Strassen on 2 n by n matrices. So I'm using n here, not n squared, right? I'm only looking at one of the dimensions of this as the input size. Okay. This is going to be well, how many recursive calls do we make if we need to compute 1, 2, 3, 4, 5, 6, 7 matrices in order to combine them up here, right? Doing 1, 2, 3, 4, 5, 6, 7 multiplications. Matrix addition and matrix subtraction, those are just done in the straightforward way, right? So there are going to be 7 recursive calls on matrices that are half as big, right? Now, how many non-recursive multiplications did we do here? We did a lot of non-recursive additions and subtractions, but each one of these multiplications right here was a recursive call to Strassen's matrix multiplication algorithm. Other than those recursive calls, we didn't do any non-recursive work here. Right? There are 0 non-recursive multiplications. So that's a simple enough recurrence there. Now we do some multiplications at some point. We have to do some multiplications at some point. When do we do the multiplications? When we get down to the end of the recursion and we've got a 1 by 1 matrix and a 1 by 1 matrix. In other words, we just have a number A and a number B, and we directly multiply them together. In other words, when you have a 1 by 1 matrix, how many multiplications do? You just do 1. Right? We don't really care about this because we've got a tool called the master theorem that we can analyze this asymptotically. Okay? So let's identify A, B, and D. A is 7. B, how much we're cutting it down each time, is 2. And D, this is it's 0, so it's bound by a polynomial of degree 0. Right? So A versus B to the D, 7 versus 2 to the 0. So this is strictly greater than, and this by case A, B, D, B to the D, right? Yeah, case 3 of the master theorem. Does anybody want to quote it? We know that mn is going to be theta of, what is it? N to the log base b of a, which is equal to n to the log base 2 of, and then a was 7. You can pull out your calculators and help me out here if you want. Otherwise, I'm going to have to look it up. What's its number? 2.807. ... Okay. So it's something along those lines. Did we do better? In total, how many multiplications did regular old matrix multiplication? Order n cubed. Did we do better? Yeah, by a little tiny amount, right? So if you're really concerned about multiplication and you want to make progress towards that lower bound, yeah, we made some progress here. But let's not forget that we blew up the number of additions, right? We went from 4 additions, right? We went from, in this case, in the 2 by 2 case, we went from 4 additions up to 18 additions. Or in the general case, we go from order n cubed additions to how many additions? So let's do that analysis as well. Let's let a sub n be the number of additions by Strassen on a 2 by 2 matrix, or not 2 by 2, n by n matrix on 2 n by n matrices. Okay? Well, this also is going to be a recurrence, right? Because ultimately we're going to be doing some matrix multiplication. Well, there's some additions done by Strassen when you do it recursively. There are going to be 1, 2, 3, 4, 5, 6, 7 recursive calls on a matrix half the size. But the way that it differs up here from the multiplications up here, we didn't do any non-recursive multiplications, did we? Here, we do some non-recursive multiplications. In fact, we do 1, 2, 3, 4, 5, 6, 18 additions on matrices of size n divided by 2. Right? If you want, this is going to be an n divided by 2 by n divided by 2 matrix. And this is going to be an n divided by 2 times n divided by 2 matrix. And when you go to add 2 matrices together, you add each component together. So we're going to end up doing 18 additions on n divided by 2 squared entries. This is the number of entries. And this is the number of additions or subtractions. Okay? So now again, we just pull out our tool. This is of the form that you can apply the master theorem to this. And this function right here, this is just going to be order n squared, right? So a, b, and d. A is going to be 7. B is going to be 2. And what is d? This is a polynomial of degree 2, so it's bound by a polynomial of degree 2. And a versus b to the d. Now we've got 7 versus 2 squared, which is equal to 4. We still have the same exact case as before. By case 3, we get that the number of additions is going to be theta n to the log base b of a. Log base b of a, that's exactly the same as before, 2.807. So it was highly deceptive, right? Take a look at this. We went from, where is it? We went from 4 additions up to 18 additions. But in the general case, we went from n cubed additions down to the same, n to the 2.807. We actually cut the number of additions because of this divide and conquer strategy. In practice, we didn't. Why? There's now this huge factor sitting out front here, right? There's a constant sitting out front here that's ignored by the asymptotic analysis. You will actually end up doing, in practice on small matrices, you're going to end up doing more additions than you are using Strassens than you are with the other one. Now, you can compute how big does my n need to be in order for that to be larger than for the constant to wipe out there, right? And it's only moderately large, more than 18 or something like that. I don't know. I'd have to actually work it out a little bit. But asymptotically, yeah, we are saving still. Even though it looked like there was a blow up in additions, asymptotically, no, it's not. We're actually saving on additions. Okay. So some other considerations here is that in practice, not all of your matrices are going to be square. Non-square matrices say that I've got a 3 by 3, right? Well, a 2 by 3. So A, B, 3 by 2, let's say, A, B, C, D, E, F, right? And I can multiply this by a 2, A, B, C, D, E, F, G, H, I, J, K, L. There we go. And that'll result in a 3 by 3 matrix, right? That's not square, and it's certainly not a power of 2. It'd be really nice if I had a power of 2, because then in my recursion, I can go 64 by 64. I'll break that up into 32 by 32. I'll break those up into 16 by 16, 8 by 8, 4 by 4, 2 by 2, until I get down to 1 by 1. Here's a trick. You can pad out with zeros. So instead of a 3 by 3, let me go ahead and go up to a 4 by 4, something that is a power of 2. I can go ahead and transform this one into A, D, 0, 0, B, E, 0, 0, C, F, 0, 0. And then to make sure that it's 4 by 4 and nice and square, I can pad out the last row by zeros. And then I'll do the same thing with this one. G, H, I, 0, J, K, L, 0, 0, 0, 0, 0, 0, 0, 0, 0. Right? There we go. And now you can go ahead and cut this up evenly so that everything is a nicely formed shape. You'll go ahead and cut this one up into quarters. All right? So it'll go from a 4 by 4 down to a 2 by 2, 2 by 2 down to a 1 by 1, and it all works out nicely. Right? Now, granted, you are doing a lot of 0 times 0 calculations. You can go ahead and check, is my matrix all zeros? If so, go ahead and skip the computation and just return back up. Because once you take this 4 by 4 and this 4 by 4, that'll result in a 4 by 4. But I can guarantee you something, right? There will that it'll have, say, x, y, z, x1, 2, 3, x2, y, z, 1. I've run out of letters. 1, 2, 3, 2, 1. I should have gone 1, 1, 1. Anyway, x, y, z, whatever. And I can guarantee you that all of these are going to be zeros, because all of these are zeros. And so they end up canceling everything out. So when you've got a 4 by 4 times a 4 by 4, that'll produce a 4 by 4. Your original should have resulted in a 3 by 3. Guess what? All you have to do is unpad. Right? Get rid of these and unpad the solution. And you recover what you actually want out of this. Now, in years past, I've assigned this as a programming assignment, and I don't think I did it this year, but it's fairly easy once you've got the hardest part about programming something like this is just making sure that all of these identities are carried through, right? that you don't actually do a plus and when you should do a minus, and minus when you should do a plus, that you get all of these correctly. And the other challenge part of the programming assignment is that you have to be able to pad it, and then you have to be able to slice it up into quadrants. So you're copying over a bunch of matrices to smaller matrices, then recombining them. Okay. I don't think I assigned this year though. Right? But that's Strassen's matrix multiplication algorithm. Again, how did he come up with these identities that worked? Well, he just wrote out the definition and then rewrote it until he found something that, okay, well, if I invest more in my additions, then I can go ahead and get rid of one of the multiplications. And if you do this recursively, it actually works out, right? That the analysis says that asymptotically you will do fewer additions and fewer multiplications. Now, that doesn't mean that this is a good algorithm in practice. The large constants that are sitting out front, as well as the additional work that you need to do to pad, cut it up, pass it off to another function, recombine those solutions, and also doing the additions, right? That constant sitting out front can be quite large. And so you need very, very, very large matrices in order for this to pay off asymptotically. And in practice, if you've got very, very large matrices, generally a lot of problems admit themselves to what are called sparse matrices, where you've got a lot of zeros everywhere. And if you've got a lot of zeros everywhere, what happens to your result? Your result is going to have a lot of zeros everywhere. And if you've got sparse matrices, there are other tricks, other structures that you can exploit to get even faster results. But the general problem has still stood to this day. I think that, do I have a year here? 36, where's page 37? Looks like, okay, I don't have any years here. But there's a Vinogard algorithm, Vinogard algorithm, that's even better. He cut it down all the way to n to the 2.375477, right? So it was cut down from 2.8 down to 2.37. Since then, the same algorithm has been reanalyzed, and a better analysis has cut it down even more, to all the way down to the current state of the art is 3.7 or 2.3727. So this is by Williams, and that was in 2012, and that was considered a huge piece of progress when she did this, because it cut it down from in the thousandths. It cut it down by 3 thousandths. Right, so that was considered big progress back in 2012 when this happened. Right, but the ultimate goal is going to be that lower bound. Right, can we do that? Right, well, can you come up with other identities and exploit those identities? Can you come up with other structures to the problem itself and exploit those structures? We don't know. There's still a gap between the best currently known and the, of course, trivial lower bound here. Or alternatively, a lot of algorithm research, this is theoretical research, is to try to prove better and better lower bounds. This lower bound is pretty clear in that you have to look at all the input at least. If you're not looking at all the input, then you're throwing something away and you're losing something. But could there be a mathematical argument out there that says you can do no better than 2.2? Right? And if you come up with a proof like that, then that starts to close this gap of the best currently known to the best lower bounds that are currently known. Right? And that's a lot of what algorithmic research is. Establishing lower bounds through mathematical proofs, establishing upper bounds through the development of algorithms by mathematical proofs of structures or analysis or something. Right? So again, this is not something that you would ever want to do in practice, but they are of prime theoretical interest, right? How well can we close this gap? Especially when you consider that matrix multiplication can be used as a subroutine to solve many other problems. If you improve on a basic algorithm over here that's used by a bunch of other algorithms, now by just improving this one algorithm, you've improved all of these other algorithms. Think about sorting. If you can come up with a better sorting algorithm, sorting is used as a fundamental tool for a lot of other algorithms. If you come up with something that you can improve sorting with, in practice that is, we've already hit the theoretical lower bound on that, right? The best sorting algorithms are order n log n, and there is a lower bound proof showing that for any comparison-based sorting algorithm, n log n is the best that you can do. So this is the best current upper bound. This is the known lower bound on comparison-based sorting algorithms. Some of you might be thinking, hey, I've heard of radix sort before, which is a linear sorting algorithm. And yes, it is, but it's not a comparison-based sorting algorithm. It's actually order kn, where n, it is linear if you consider k, the length of any of your elements that you want to sort is bounded by some constant, right? That's not a comparison-based sorting algorithm. Comparison-based sorting algorithms, you've got this lower bound, you've got this upper bound, they match. So you can provably do no better than, say, merge sort asymptotically. Of course, in practice, you can do better. Does anybody know what sorting algorithm Java is using currently? Or has used in the past? Nobody knows? Up until Java 7, they used a modified merge sort, where they did use merge sort, but when they got down to a certain size, they switched over to insertion sort. So it was a hybrid merge sort. Java 7 or Java 8, yeah, I think it was Java 7, they switched over to another one called tim sort. Asymptotically, it was the same. It's still order n log n. But in practice, it performed better. Like if you looked at the empirical analysis of it, it performed better. All right, it was stabler. It was, I don't know if you can say that it was simpler or not to implement, but they did switch over because that sorting algorithm was actually developed by Tim when I forget his name. Tim. It's on the tip of my tongue, but it was created for the Python programming language, and since then it's been ported over to Java as the de facto sorting algorithm. So you can always come up with practical improvements. Sometimes you can come up with theoretical improvements. Sometimes the theory tells you that you cannot improve on it asymptotically at least. Okay? All right. Any questions so far? All right. I was hoping to get to an example here of what we're going to do next. I will go ahead and I'll give you the truncated example of it, though. This all ties into matrices as well, though not matrix multiplication. Something different in matrices. 3x plus 2y is equal to 35. X plus 3y is equal to 27. Right? Now, we'll forget about matrices for a second. What is this thing right here? It's a linear system, right? There are two equations in two unknowns, x and y. If I only had one equation, and I asked you to solve this, would that be reasonable for me to ask you? One equation, two unknowns, can you solve it? It's an indeterminate system, right? That if you set one of these variables, then that determines the other variable. It's free, right? It's a free variable that you can set to anything. But if I gave you two equations that have to be satisfied in this linear system in two unknowns, now it's probably a determinate system, right? That you can determine the values of x and y. Help me out. How do I solve for x and y? Okay. X is equal to 27, and then take 3y to the other side. All right, now I've got a solution for x. It's just still indeterminate, but I can go ahead and plug that in up here, and I get 3 times 27 minus 3y plus 2y is equal to 35. When I do that, what do I get? 3 times 27, 81, thank you, minus 9y plus 2y is equal to 35. So this is 7y. Take this over to the other side. This is going to be 45, 46. Is that right? And then, so y is equal to 46 divided by 7. Unfortunately, I should have chosen my numbers better so that it came out to a nice, usually when you give linear systems like this, you make it so that everything comes out to a nice integer in the end, but I didn't do that here, right? So now that I've got y, well, now I can go ahead and plug that back into the other equation, and I get that x is equal to, well, this one up here, 27 minus 3y, which is going to be 46 over 7, and at that point you can take out your calculator and figure out what it is, right? So 2 equations, 2 unknowns. I'm not going to write it out, but, well, okay. That was 2 equations, 2 unknowns. What if I gave you a linear system with 3 variables? What would you have to do then? So let me go ahead and just make a system up. X plus y plus z is equal to 5. 2x plus y minus z is equal to 7. 3x. Maybe we don't have a y. The coefficient here is 0 instead. Plus 10z is 17, right? I'm choosing prime so that it'll actually work out. What are you going to do now? 3 equations, 3 unknowns. What do you have to do? Take these onto the other side, solve for one of these variables, plug it in over here. That gets you down to 1 equation with 2 unknowns. Then you have to solve for another variable and plug it back in up here. That takes it down to 1 variable, 1 scalar value that solves for 1 value. Once you've got your x value, what do you then do? You go back and you plug that in and into the equation where there's only 2 unknowns. That gives you a solution for y. And then you plug that into to the last equation. You plug both of those values in over here, and you end up with a solution for z. Right? What happens if you do it for 4 variables? You probably all had some. You've seen this before, right? Has any math professor ever given you a system this large to solve by hand? Yes? No? No, that's kind of, okay. What about if 50 variables? Would that be reasonable to do by hand? No, you'd quickly lose the forest for the trees and you would make a mistake somewhere, right? But we can do it with a computer, right? How are we going to do that with a computer? We need to codify this process of taking one variable, solving for 1 variable, putting everything onto the other side, then putting that into another equation, putting everything onto the other side so that we have now, we go from n variables down to 1 variable, down to n minus 2, or sorry, n variables down to n minus 1 variables, down to n minus 2 variables, down to n minus 3 variables, until we get down to 1 variable. Once we've got 1 variable, then on the other side of the equation is just a number. We've solved for that variable. Now we need to go back in the process, plug that in, solve for the next variable. Plug those 2 in and solve for the 3rd variable. Plug those 3 in and solve for the 4th variable. Right? And that's the description of the algorithm that we'll look at on Monday called Gaussian elimination. Right? And you might have seen this if you've taken a linear algebra course. But again, if you've taken a linear algebra course, they've probably never given you a system of more than 3 variables. Right? I'm going to give you a system of 50 variables, 100 variables. Do not do them by hand. Instead, you'll be programming this. Okay? And you'll solve systems of linear equations of 100 variables, 1,000 variables. Right? Not only that, but you'll be able to tell whether or not a system is determinate or indeterminate. Let me give you one more example before we move on to the quiz here. X plus y is equal to 2. 2x plus 2y is equal to 4. Solve this system. Let's go through the process again here. I'll take y onto the other side. X is equal to 2 minus y. Plug that in down here, and I get 2 times 2 minus y plus 2y is equal to 4. Okay. Well, this is 4 minus 2y plus 2y is equal to 4. These two cancel each other out, and wow. Did you know that 4 was equal to 4 before today? Right. So, what is x? What is y? Who knows, right? This is an indeterminate system, right? What does it look, if I were to graph, now these are only two variables, so you could graph them in the plane. What are these two, let's say y is equal to negative x plus 2. Graph that. What does that look like? The y-intercept is 2, and it's a negatively sloped value, so it goes something like this. I missed my own mark. There. What about this one? Well, it'll end up with let's go ahead and 2y is equal to negative 2x minus 4. Take 2 onto the other side, what do you get? Negative x minus 2. Hey, that looks familiar. What's the second equation? It's exactly the same one. Now, what's the interpretation of this system right here? The interpretation of this system of this one is that at this x coordinate and at this y coordinate, these two lines meet. So how many solutions are there here? How many these two equations meet at how many lines or at how many points? Infinite. There are an infinite number of solutions that will do this. In other words, I don't have two equations and two unknowns here. I only have one equation and two unknowns, meaning that it's not solvable. Right? There's another degenerate example. Yeah, let's do it. X plus y is equal to 2, and then 2x plus 2y is equal to 5. There we go. I'll let you graph these out for yourselves. It's going to look something like this. Both of these lines are going to have the same slope, but different y-intercepts. Right? Now, if the interpretation of a solution to a linear system of linear equations is where they meet, how many solutions are here? These are parallel lines. Do parallel lines ever intersect? Nope. So there are 0 solutions. And again, if you go through this process of solving this thing, let's go ahead and try it. Let's go ahead and take x is equal to 2 minus y, and we'll plug that in over here. 2 times 2 minus y plus 2y is equal to 5. So 4 minus 2y plus 2y is equal to 5. These cancel out. Hey, I learned something else today. That 4 is equal to 5. Is that true? No. That's because these lines don't actually ever intersect. There is no solution at all. You get, is this true or false? This is false. What do you get? What do you call that? A contradiction, right? So if you started by assuming that these two lines intersected somewhere, you would eventually get a contradiction, right? And you would know that there's no solutions at all. So how do we account for both of these degenerate cases where we've got an infinite number of solutions where they intersect everywhere versus 0 solutions versus 1 solution? Right? And the same algorithm is going to be able to tell us all of that. Okay? All right. This is where the recording will stop. So any questions?